All right, hello everyone, and welcome to another one of Mr. Martin's math videos. This is a video for uh, Canadian, British Columbian Pre-Calculus 12 math curriculum. We're looking at Chapter 6, Section 2, which is talking about the sum, difference, and double angle and identities in our trigonometry unit. So at this point, it would be useful to create an identity toolbox, something that you have with you that you can refer to as you're proving your trig identities or your trig expressions that you're being provided with. So this toolbox will keep all of your known identities in one place and give you the resources necessary to prove some of the other identities that you'll come across in the near future. In that toolbox, you'll need to add the quotient, reciprocal, and Pythagorean identities that you've learned in 6.1. You should also add the following new identities for this section. And so if you look on your formula sheet, you already have all of these trig identities on there. Okay, so when you're doing your homework or any one of these assignments, have that paper out as a reference because you're going to need to be referring to it probably more now than any other section in this course. And so make sure to have that handy. If you want a copy of the one that I use, you can ask me on Teams or drop a comment on the video, and I can maybe share one in the video description. So let's take a look at some of these new identities that we're learning. So yes, last class we looked at these three here. We had quotient, reciprocal, and Pythagorean identities that we applied in a couple of examples. Today we're going to add a bunch more kind of complex looking ones. We're not going to talk about the proof behind each of these. They're just trust that they have been proven and they're trustworthy. They have their own set of proofs, and so we can use these now to prove other trig identities. So the first ones are the sum identities. So here, sine A plus B is equal to sine A cos B plus cos A sine B. Cos A plus B is cos A cos B minus sine A sine B. And then tan A plus B is tan A plus tan B over 1 minus tan A tan B. So some of these, are a little bit funky, a little bit different looking, but we're going to be finding these in the trig identities you'll be asked to prove. And so these will be valuable tools. Differences identities, look very similar to the sum, except for the signs have been changed. Okay, essentially exactly the opposite in terms of the sign from one to the next. And so in these first two, you really, when you do a substitution, when you're using these identities, you really want to make sure that you're being careful with the signs. Okay, it's easy to put a minus where a plus is supposed to be, or a plus where a minus is supposed to be. So really kind of double check your signs, triple check to make sure you don't make a silly mistake. Okay, very important there. It's a very common student mistake. All right, and then there's the double angles. Double angle identities here when you have sine 2a or cos 2a or tan 2a. All right, sine 2a gives you 2 sine a cos a. Cos 2a has three options here. Okay, so all three of these are proven identities. So cos 2a can either give you cos squared a minus sine squared a, or 2 cos squared a minus 1, or 1 minus 2 sine squared a. Okay, so so this one is one that you can go three different directions, and so the one you choose should be based on everything else you have in the question. Okay, and there's gonna be some trial and error here, and there's gonna be different ways of doing this. Okay, you might find one way, and then you ask your friend about it, they did it a different way. That's totally to be expected in these kinds of problem. And then tan just gives us 1 is 2. Tan 2a gives us 2 tan a over 1 minus tan squared a. Again, we're not going to go over the proofs of these. They have been proven, and now we're going to just use them to prove other ones. Okay? We skipped over these, but there is justification for them. If you're interested, check out Khan Academy or other internet resources for sufficient proofs. I can print off one of these proof summaries as well if you're interested. All right, so let's now actually get into some examples here for these types of problems. All right, so first we're going to look at, again, starting with our non-permissible values. Okay, non-permissible values. Okay, NPVs, right? Oh, I gotta make my cursor, my pen a little thicker. NPV, all right. So in this situation, I know that my denominator cannot equal 0, or else my fraction is going to give me undefined, right? And so here, sine 2x cannot equal 0. Okay, so in this situation here, we have 2x which is equal to, so yeah, I'm going to use the inverse sine, so arc sine on both sides here. That's going to be 2x is, so cannot equal to, we're going to use it as an equal sign as we're solving this. So sine, or arc sine, 0. Okay, so in this situation, at what degrees is sine equal to 0? Okay, is the y value, that ratio, that sine or your trig ratio equal to 0, specifically the y value of the point equal to 0? At what angles? That would be at pi over 2. And where else? Sine is equal to 0. No, wait. Sine is equal to 0 at 0 and at pi. Okay, at 0 and at pi. So let's do this. 2x cannot equal 0, and 2x cannot equal pi. Okay, and the next one would be, if you wanted to go around the circle a second time, 2x cannot equal 2 pi. Okay, but we got to solve for x still. So now we divide both sides by 2. And I'm doing lots of these so that we can come up with a general formula. Okay, so here x cannot equal 0. Here x cannot equal pi over 2. And here x cannot equal pi. Okay, so we see that for our general formula for non-permissible value, we could say x cannot equal 2 pi and multiples of 2 pi n, where n are integers. Okay, so that would be my non-permissible value there. Okay, so you do have to find the non-permissible values even in these, kind of denominators. And so just kind of go through it one step at a time. Solve for a couple, rotations around your unit circle so you get a better idea of the general formula that describes that non-permissible value. Okay. Now that we found the non-permissible value, let's actually simplify this expression. So 1 minus cos 2x is equal to sine 2x. Okay, now before, kind of our trick was, you want to change things from cotangent and cosecant and all these things into sines and coses. So that's still the case here where those appear. But we're going to be dealing with a lot of double angle proofs as well. A lot of them that you'll be dealing with. The sum and difference identity here are used much less than these double angle identities. And so most of the time you'll be working with these. These are two-way identities. Okay? These are two-way identities. However, most of the time when you're simplifying, you'll want to be moving left to right. Okay, so changing things on the left to things on the right and then simplifying from there most of the time. Can't say all the time, but the majority of the time you want to be moving left to right as you're proving your identities. So in this situation here, I can start reducing this. So 1 minus, I'm not sure what I'm going to do at the top yet. I'm going to do the bottom first. And sine x, I only have one option for sine x. It's 2 sine a cos a. So I'm going to do that. 2 sine a cos a. All right. Now, based on that, which one of the cos 2x double angle identities do I want to use on the top? Okay, and here there's different approaches that you can take. I'm going to go with the 1 minus sine, 1 minus 2 sine squared a. Okay, 1 minus 2 sine squared a. Okay, actually, let me write my substitutions in red. So 1 minus 2 sine squared a, just so that you see it, and this becomes, what was it, 2 sine, oh, I shouldn't use a, sorry, I should use x, 2 sine x cos x, and this we're dealing with an x as our variable, not a, okay, but same thing. All right, so now I've substituted that. I'm going to clean up that top row a little bit just because, I got some brackets and stuff. So this becomes 1 minus 1, okay, which is going to disappear, and then this becomes positive 2. So this becomes 2 sine squared x over 2 sine x cos x, okay. Now I can cancel some things out in this situation. So the 2's cancel out here. The sine squared x, here you need to see this as sine x times sine x. And so the sine x cancels out the squared, and that leaves me with sine x over cos x, which would be equal to tan x. And that would be your final simplified answer for this trig identity or expression that they gave us. Okay? Yeah, kind of seems a little bit okay. And again, we could have done this a different way, but this is the way that we chose to go. Okay? All right. And we can verify that answer is correct by choosing a permissible value and substituting it into the original expression and the answer. So the original expression, so let's see if we can find that, how to plug that into these equations here. So here I have 1 minus, let's choose x is equal, for the test point, I'm going to say x is equal to 1. Okay, that's a permissible value, right? Yep, totally a permissible value. So let's plug that in here. On the top, I have, going all the way back to my original equation, this here, I have 1 minus cos, and then 2 times 1, right? Bracket divided by sine 2 times 1. That's equal to that. And then if I say tan 1, I get the same thing. So they are equal to each other. Okay? All right. Let's try another one. Okay? And you'll see these are just going to come. You'll get the hang of these as we go. All right. So first, got to start with our non-permissible values. All right. So again, that denominator cannot equal 0. So that's what I'm using here. So cos 2x plus 1 cannot equal 0. cos 2x cannot equal -1. 2x cannot equal arc cos -1. So 2x cannot equal, let's take a couple things. So where is cos equal to -1? Okay, well, within the first cycle, that's equal to pi, right? Cos is equal to -1 at 180 degrees, or pi, right? That's where your x value is -1. So this is at pi. And again, this would happen again, just so that I can get a better idea for my general equation. This would happen again the next time around the circle, which would be 3 pi. Okay? Oops, I made a mistake in my notation here. This shouldn't be 2 pi, it should be 2x. And last step, I divide by 2, both sides. And I get x cannot equal pi over 2, and x cannot equal 3 pi over 2. All right, so the fact that I used 2 here, it was helpful because first it gives me an initial value to start my general solution. Sorry, this is not times n. And it gives me a rate of change on my non-permissible value. So this would be plus pi n, where n is an integer. Okay, it's not just it's not just the multiples of pi over 2 here, because there is a difference of pi from one value to the next. Okay, so the next value, so that's, I have to represent that in my general equation. So this would be my non-permissible value. So that's just our non-permissible values. We haven't done our proof yet, but just so yeah, hopefully these are becoming more and more familiar and automatic for you guys. So let's start this, simplifying this expression here. So 2, sine, let me start over here. Sine 2x over cos 2x plus 1. All right, so again, I want to substitute sine 2x into its trig identity here. Okay, I'm just going to look over. I'm not going to scroll up each time. Have your formula sheet out for this lesson, and it'll help you. So 2 sine x cos x is equivalent to that sine. I'm just working up and down. Okay, I'm working like this. And which of the 3 am I going to use this time? I'm going to use the... we can try things, right? And so let's try 2, instead of cos 2x, I'm going to try 2 cos squared x minus 1, and then plus 1. All right. So now let's, this should be in blue, plus 1. Okay. So that's just from one of the 3 possibilities for that cos 2x double angle. So let's start simplifying this. So 2 sine x cos x is equal to, that minus 1 plus 1 cancel out. I get 2 cos squared x. All right, and again, simplifying just like last time. I'm going to cross out the 2's, and the cos crosses out the cos squared on the bottom, and I end up with sine x over cos x, which, lo and behold, again, I get tan x as my solution. Okay, now just to show that, there's different ways of doing this, I'm going to do an alternative path. Okay, so here at this stage, sine x cos x, instead of using double angle the 2 cos squared x minus 1 plus 1. I'm going to try the other one, the one I used last time, which was I'm not going to use the cos squared x minus sine squared x because I'm not going to be able to simplify that very well. All right, so here I have 1. I'm going to substitute. Okay, so this is an alternative path. I'm going to substitute 1 minus 2 sine squared x plus 1. All right, now I'm going to simplify some of this. 2 sine x cos x over, I'm going to have 1 plus 1 is 2. So here I end up with 2 minus 2 sine squared x. Now I can't just do 2 minus 2 because that 2 times sine squared x is multiplied to the sine squared x before it's subtracted, right? And so here, one approach I could use for this is using multiplying the top and bottom by a conjugate, and eventually you could get to the same answer, but it's going to get more complex, okay? And so the fact that this one simplifies so nicely and this one gets messy very quickly is kind of the paths that you want to be able to recognize. So you kind of want to plug in the different options and see how messy or how nicely things simplify based on what you choose, okay? But in the end, you can still get to the same answer, but one is definitely easier than the other. All right, and you just gotta look. All right, so with that, I want you guys to try some on your own, okay? For these ones, don't worry about non-permissible values. Make sure you know how to do those, okay? But just jump right in here and with your double angles. All right, so go ahead and pause the video. And these are the 4 that I want you guys to try on your own, just on a piece of paper, and then we'll unpause the video and do them together. All right, hopefully that went well for you guys. So let's get started here. So first I got that sine double angle, so I'm going to substitute that with 2 sine x cos x. And the bottom, I don't have to simplify or anything. This isn't a double angle. I'm just going to do 2 cos x. All right. The 2's cancel out here. The x cancels out here. And I get sine x as my solution. Or sine theta. Here, let me just substitute all these x's for thetas. 2 red ones at the top. Sometimes they'll use x, sometimes they'll use theta. Sometimes they'll use a, like in our reference table at the beginning, they were using a. In the end, it's all the same. It's just a variable. Okay? So my final answer would be sine theta. All right. Moving over. This one here. So I have 2 cos theta on the bottom again. What would I have on the top? What would I have on the top here? Let's see the different options. I could do I'm not going to use the sine squared x or minus cos squared x. I'm going to use the 2 cos squared x minus 1 because it's minus 1 plus 1. So those ones will cancel out. And then I'm going to, I guess another trick that you're looking for is you're trying to figure out how to turn polynomials in these into monomials, because monomials are much easier to divide and simplify than when you have a bunch of polynomials left over. So if you can get a double angle kind of substitution that reduces your polynomial to a monomial, whether it's in the numerator or denominator position, that's a really good place to start in terms of knowing which one to try out. Okay, so for example, with that in mind, I'm going to substitute 2 cos squared x minus 1 plus 1 over 2 cos, again, theta. And this is this is a mistake I'm going to make a lot. So theta. Okay. So now the -1 and the +1, they just go away. It's awesome. And I end up with 2 cos squared theta over 2 cos theta. And the 2's cancel out, and that cos theta on the bottom cancels out one of the coses on the top, which just leaves me with cos theta on the top. Okay, now I think you probably both of these have the same denominator, so I will do the non-permissible values for you guys just so that you can see another example of it. So here both of them have a denominator of 2 cos theta, which cannot equal 0. All right. First thing I do in this situation, because the 2 is in the front, I divide both sides by 2. So cos theta cannot equal 0. At what angles does cos theta equal 0? Right? Cos theta equals 0 at pi over 2 and 3 pi over 2. All right? So theta cannot equal pi over 2 and 3 pi over 2 and lots of other ones in the future, right? So here your theta would cannot equal, your general term would be pi over 2 plus pi, because there's a difference of pi between those two values, plus pi n, where n is an integer, both positive and negative numbers. So this would be your non-permissible values for both problems on the top row here. Okay? Let's try another one here. This one doesn't have a denominator, so don't have to worry about that in this situation. We're going to do some substitutions here. So the substitutions on the right, because it's sine squared x, I only have one double angle identity, trig identity for sine squared x, and sine 2x. So I'm going to plug that one in right away. So this is going to be plus 2 sine x cos x bracket times sine x. Okay. And I'm going to kind of play that one out to see where I end up with. And so I multiply the sine x into the 2 sine x cos x. I get 2 sine squared x cos x. Okay. So the fact that I get that 2 sine x squared, that's going to give me a hint for what maybe I should do on that left side. Okay. Since I get that sine squared x, I'm going to substitute this with the one that has 2 sine squared in it. So I'm going to substitute that one with 1 minus 2 sine squared x times cos x. All right. And I end up with, here I have to distribute the cos to the 1. I end up with cos x minus 2 sine squared x cos x. I'm so happy they're using x. And lo and behold, these just cancel each other out, right? Negative 2 sine squared x cos x, positive 2 sine squared x cos x. So these just cancel out. And I'm left with my answer of cos x. Lovely. Okay. All right, so let's do this one here. I have a cos squared x on the top, and I have cos 2x plus sine squared x on the bottom. In this situation, the top, I need to leave that as is, okay? Because it's not cos 2x, it's cos squared x. They're different, okay? All these trig identities here, these are all cos 2a. It's 2 times a. It's not cos a times cos a. Okay, so make sure that you're not confusing those. And in this situation, I think I'm going to do this one for this bottom one because I have minus sine squared or a plus sine squared in it. And so I think those might cancel out well. So let's give that a shot. So in my denominator, I'm going to substitute cos squared x minus sine squared x, bracket, plus sine squared x. Okay. There's no multiplication here because it's a plus. So the minus squared x and positive squared x, they cancel out. And the cos squared x on the top and the cos squared x on the bottom that's left over, they cancel out. So my answer here is 1. Isn't that wonderful? Isn't that so satisfying? Hopefully you feel as strongly about that as I do. So those are some problems there. You're gonna have, hopefully those went well for you. You're gonna have lots of questions from your homework, I'm sure. So make sure you do your assignments so you bring lots of meaningful questions to our next class together. Now let's look at a third example here. Notice we haven't used the sum identities and the difference identities. That's very common. We don't use them that much, but they are used in these types of problems, okay, that we're setting up right now, okay? So you'll get a sense of how we use those. So here, pardon me, using our unit circle, we want to know the exact values of the following expressions. So the expression sine pi over 6. So at pi over 6, what is the y value? Look in your unit circle, you see as the y value is 1 over 2. Okay, we know this. We've done the unit circle. You guys have it memorized, or you did. Cos at an angle of 135. Okay, an angle of 135 is 45 degrees past 90 degrees. Okay, where the x and y value are equal to each other, and they're both equal to, well, the y is equal to positive square root 2 over 2, and the x is equal to negative square root 2 over 2. Okay, tan 300, 60 minus, 60 less than 360. Okay, so in this situation, the y value would be y over x, right? The y value here at that stage is negative square root 3 over 2. And the x value is 1 over 2, right? So that equals negative square root 3 over 2 times 2 over 1. And we end up with a value of negative square root 3. Okay. Again, that's chapter 4 in the textbook that we've done already. And last one, sine pi over 12. Is pi over 12 on the unit circle? No, it is not. Okay. However, we can use what we know about the unit circle to still solve for this in exact values. Because here, I can take my calculator with the best of them and just plug in numbers, right? This is my calculator in radians. So here, pi divided by 12. Oh, the answer is 0.258, blah, 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 right? But here, we want exact value answers, okay? So here, we're actually going to utilize one of our sum identities to solve this, okay? So I don't know what sine pi over 4 is, okay? However, let's see if we can rewrite the sine pi over 12. Let's see if we can rewrite pi over 12 into the sum or difference of two known angles on the unit circle. So, for example, we can rewrite we can rewrite 7 pi over 12 as pi over 3 plus pi over 4. Okay, and then we could use the sum identity sine A plus B, which is sine A cos B plus cos A sine B, to find the value of sine 7 pi over 12. So if we can do that for 7 pi over 12, can we do that for pi over 12? Okay, and they give you a big hint here. Okay, well, pi over 12 is not equal to pi over 3 plus pi over 4, but it is equal to pi over 3 minus pi over 4. Okay, I'll just give you a second to confirm that in your brain. All right, common denominators, you end up with 4 pi over 12 minus 3 pi over 12 gives you 1 pi or pi over 12. Yes, it's confirmed. Genius, right? Here, just to show it out, here it'd be over 12 minus 3 pi over 12, right? Okay, so this works. All right, so instead of using this sum identity of sine A plus B, I'm going to use the sum identity, the difference identity of sine let me just break it down one step before. So in looking for sine pi over 12, that's going to be equal to the sine of pi over 3 minus pi over 4. Okay, we just proved that over here. Okay, and if I look at my trig identities, okay, on the first page or in my formula sheet, all right, I know that sine, and so you have to see this as sine A minus B, okay, and sine A minus B is sine A cos B minus, I think, cos A sine B. Okay, I'm just going to confirm that. Go ahead and confirm it for yourself. Sine A cos B minus cos A sine B. Awesome. Okay, so now I'm going to plug in, I'm going to distribute these values into this difference identity. So sine, then my A value is pi over 3, then cos pi over 4 minus cos pi over 3, and then sine pi over 4. All right, and now I can simplify this, right? First of all, I can change each of these into exact values on the unit circle. Okay, so for example, sine pi over 3. What is the y value for pi over 3? That's on your unit circle. The y value for pi over 3, the point on the unit circle for pi over 3, is square root, let me substitute that in red, is square root 3 over 2. Right? Does that make sense? Let's do the next one. What about cos pi over 4? What is the x value of pi over 4? It is square root, why am I in green again? Square root 2 over 2. All right, you see where we're going with this? Now, what about for cos pi over 3? Well, that is 1/2 on your unit circle. And the last one, let's use this one. Last one here would give me sine, I want to get the colors just right, would be square root 2 over 2. Right? Does that make sense? Were you able to track that? If not, kind of go back and slow it down, rewatch it, and make sure you can track all of 4 of these spots on your unit circle. So now we've substituted a bunch of values, and all of them are exact value. So as long as I'm not plugging things into my calculator, but I'm actually doing the math, I'm going to get the right answer. Okay? So first I'm going to multiply the 2 expressions on the left. Root 3 times root 2 is root 6 over 2 times 2 is 4, minus 1 times root 2 is root 2, and 2 times 2 is 4. And here, I already have common denominators, which is nice. And I end up with root 6 minus root 2 over 4. And that is what sine pi over 12 is equal to. Okay? So even though pi over 12 was not on our unit circle, because I could find two numbers, two angles that added to each other, or the difference between them, which were on the unit circle, I was able to then use in this case, the difference identity to find the exact value of an angle that was not on my unit circle. Okay, so this is a very common question you're going to see for using these sum identities or difference identities. Okay, you're not going to see them as much in simplifying or proving these types of equations, though you will see them. Okay, don't completely bar them off of your toolkit. Okay, but these are more common applications for this. Your homework on the bottom here, due Monday. And hopefully this video was helpful for you. Watch it as many times as you can, as you need to. All right, and make sure you do this homework for Monday, so you're coming with meaningful questions, because then we're moving on to 6.3, and things really start to build and accelerate here. Okay, so you guys have a great day, and we'll see you next time.